Okay, we're going to be looking at this question. So, a student investigated the effects of the size of marble chips on the rate of reaction between marble chips and hydrochloric acid. So, I'm going to underline my key points here. So, the student investigated the effects of the size of marble chips on the rate of reaction between the marble chips and the hydrochloric acid. So that means my two reactants are my marble chips and my hydrochloric acid. So these are my reactants. This is the method used. So they added 10 grams of marble chips into the flask. They added 50 centimeters cubed of hydrochloric acid and they started the timer. They recorded the mass loss from the flask every 10 seconds. They then repeated steps 1 to 3 with different sized marble chips. Okay, and this is the apparatus below. Draw one line from each type of variable to the correct example of the variable. So the first one we've got here is our independent variable. Now we know our independent variable is the thing you change. So we know already that the thing that she's changing is the size of marble chips because she repeats it with different sizes of marble chips. So the thing you change is the size of the marble chips. Now your control variable are the things you keep the same. So the things you keep the same. Now, we're not trying to keep the mass loss from the flask the same because that's the thing we're measuring. We don't want to change the size of the container because that might spread things out a bit too much. We know it's not that one because that's our independent variable. We're not trying to see what the time taken is, that's what we're trying to record. So the thing we must be keeping the same is the volume of acid. Okay, because if we change our volume of acid, we could be changing or affecting our rate of reaction. So the thing we need to keep the same here is our volume of acid. Our next step here, so the equation for the reaction is calcium carbonate plus our hydrochloric acid so the equation goes to calcium chloride, water, and carbon dioxide. So you need to name the 3 products. Now, we've already said that our reactants are the marble chips and hydrochloric acid. So we've already said that our calcium carbonate, because that's what marble chips are made out, and our hydrochloric acid are a reactant. So we said that at the top over there. That must mean our products are going to be our calcium chloride, water, and carbon dioxide. Remember, if there's a 2 there, it's going to be dioxide. So we've got calcium chloride, water, careful not to put hydrogen dioxide, and carbon dioxide. Another student suggests putting some cotton wool in the top of the flask. Suggest why this improves the investigation. Well, obviously, if you put something on the top, it's going to stop things from escaping. So it's going to stop the loss of things like water, liquids, or the loss of the acid. And it will, but because the cotton wool is porous, it's still going to allow that gas to escape. So it's still going to allow for the change in mass to occur, and that's only going to allow the gas to escape, not any liquid. So using it stops the loss of liquid. Okay, the reaction produces 1.6 grams of gas in 30 seconds. You need to calculate the mean rate of reaction in the first 30 seconds. Now, you've been given the equation, you just need to plug in your numbers. So the mass of product produced in grams. Now, we've just been given this is going to be 1.6 grams, and then divided by our time, so 30 seconds. So you're going to have to use a calculator for this unless you're very good at mental maths. So you've got 1.6 divided by 30 seconds. Press this S to D button here if you get a weird number like this, and it gives you your answer. So we've got 0.053. This little dot here means it's recurring. Okay, so you don't want to round that or change it, you need to do it like that. What is the unit for the mean rate of reaction calculated? So for part D. So up here we need to work out what the unit is. So you need to tick one of the boxes. So it's going to be grams, grams per second, second, or seconds per gram. Now, a nice way to work this out if you're not too sure is you look at the units up here. Now I can see my gram is on the top and my seconds are on the bottom. So that means I'm going to get grams per second. So it's going to be this box here. Again, only tick one box. You tick more than one box, you won't get the mark. Okay, so the table below shows the students' results. So we've got the time in seconds and the mass of gas produced in grams. You need to plot the data from the table above in figure 2, so this thing here, and then draw a line of best fit. So I'm going to put that so we can see it. And it focused, yay. Okay, so time in seconds at 0, 0. So 0 seconds, I had 0 gas produced. So my point will be here. You again go along to the 10-second line, that's here. And at 10 seconds, it was at 0.8. Now, if I look at these units here, I can tell they're going up in 2. So each 2 boxes is worth 0.1. So if I go here, this is 0.6, 0.7, 0.8, 0.9, and we get to 1. So if I'm at 10, I go all the way up to where I meet the 0.8. So that would be here. At 20 seconds, so we go to the 20 now, it was at 0.6. So 20, go up to 0.6, so this is 0.5, 0.6. At 30, we want to go up to 1.6. We're going all the way up here. This is 1.5, and 2 up, because remember each 2 boxes is worth 0.1. Will get us to 1.6. At 40 seconds, we need to go to 1.8, so go all the way up. So this is 1.5, 1.6, 1.7, 1.8. At 50 seconds, we're going to go all the way up to the 2. And at the 60 seconds, we're going to go all the way up to the 2. Now, looking at this, I can tell that there must be an anomaly. Okay, the reason I can tell there's an anomaly is because all these points fit a pattern except this one here. So this makes me think that this one here is an anomalous result. So it does not fit the pattern, and there must have been some sort of mistake or error at this point. Now, for this line of best fit, I'm not going to be drawing a straight line. Okay, that's because if I draw a straight line, it's going to completely ignore these points here. And because these points level out, it makes me think that the reaction must have stopped occurring. Okay, because no more gas is being produced. So for this line of best fit, I need to draw a nice curve. So we want to encompass as many. I'm not connecting the points, okay, because you do not connect the dots when you draw a line of best fit. And you draw a nice curved line of best fit. Figure 3 shows large marble chips and 8 small marble chips. This is my large one, these are my small ones. The large marble chip has the same total volume as the 8 small marble chips, but they have different surface areas. Why do the 8, so they have the same total volume, but different surface areas? Why do the 8 small marble chips react faster than the large marble chip? So these ones are faster than your large marble chip. Okay, so you've got to tick the box. Okay, again, you're only ticking one box. If you tick more than one, you won't get the mark. The 8 small marble chips have a larger surface area, so less frequently collide. Okay, that doesn't make sense because if you have a larger surface area, you're going to collide more often because there's more things to collide into. The 8 small marble chips have a larger surface area, so more frequent collisions. This sounds likely, so I'm going to keep that one in mind. The 8 small marble chips have a smaller surface area, so less frequent collisions. So I know my 8 small marble chips have a larger surface area. Just like when you break something up, there's more area for each thing to be hit by. Because just think, the bits inside the large marble chip, they haven't got contact to the things around it. So I know my 8 small marble chips have a larger surface area, so I know it can't be that one. The 8 small marble chips have a smaller surface area, so more frequent collisions. Again, I know they have a larger surface area, so it can't be this one, which means it must be the 8 small marble chips have a larger surface area, so more frequent collisions.